Okay, today we're going to start talking about something called the kinetic molecular theory. In the kinetic molecular theory, if you look at the name, just break it down into its parts. Kinetic, and I know you guys have already studied kinetic energy, which is the energy of movement, and molecular, so this has to do with something called a molecule that we'll talk about here in a minute. But basically, this idea has to do with the movement of molecules in the different types of matter that we have. And as we go through the different phases of matter, the movement of the particles changes. So this theory tries to actually explain how matter behaves, and it does that three ways. The first way is it states that matter is made of small particles. This could be atoms, this could be molecules, or this could be ions. Now, atoms we talked about in the last unit, and you guys should know hopefully what those are. Molecules are simply atoms that are stuck together chemically, okay? Like water has two atoms of hydrogen and an atom of oxygen bonded together to form a molecule of water. Ions we also talked about last unit. Remember when we did the nuclear notation and we were trying to find out if that atom had a charge on it? We would take the number of protons minus the number of electrons, and that would give us a charge. Anytime that we had a number that was not zero, then that atom had a charge, and we could say that that is no longer an atom, it's actually an ion. Now, the second part is that these particles are in constant random motion. So they're always moving, and we really can't predict how they're going to move necessarily, in which direction. But we can kind of predict to a certain extent, based on certain properties, how the movement is happening. And the third part is that these particles collide with both each other as well as the walls of their container. Now, solids, that's really easy to see because the particles are so tightly packed. So of course if they vibrate a little bit, they bump into their neighbors. Liquids are still attached, and yes, they roll and slide past each other. Well, that's colliding with each other. And gases, even though they're pretty far apart space-wise, they do come in contact with each other. They do bounce off of each other. And in terms of the walls of their container, we actually really talked well about the gases and how they do that. And that's what actually creates pressure. Liquids and solids do this as well. When they're inside of a container, that vibrational energy that they have actually pushes up against the wall of the container as well. Now, the energy that is in here can be one of two types. We have thermal energy. And thermal energy is actually really hard to measure because it is the total energy of the particles. We can measure a lot of the different bits and pieces of this thermal energy, but to truly get the total energy is kind of difficult actually to do. Now, this includes the energy that the particles have through their vibrations, and also the energy that actually holds them in place when they're in a particular phase, whether it's a solid, a liquid, or a gas. Now, one of the other types of energy that's actually more convenient for us to use is kinetic energy. And like we said before, that's the energy of movement. All right, specifically when we're talking about states of matter, we're wondering how fast the particles are moving. So how can we conveniently measure that? Well, what scientists do is they actually measure the average speed, because if you have a piece of matter, you can have millions and billions and trillions of molecules, and a lot of them are going the same speed, but many of them are also going different speeds. So they measure something called average kinetic energy, and we have turned this average kinetic energy into a form that's more convenient for us, and that is temperature. Temperature is the average kinetic energy, or the speed of particle movement. Now, theoretically, this motion stops at a temperature called absolute zero, which is 0 degrees Kelvin or negative 273 Celsius, which we talked about again in our first unit. Now, how does this idea of the kinetic molecular theory and these types of energy that matter can contain actually relate to what we've already talked about? Well, what this allows us to do is understand why matter undergoes phase changes. Okay, so changes in state, like for instance solid to liquid, are due to changes in the kinetic energy of the particles. I can have something that's a solid at room temperature, let's say wax, like candle wax, and I can actually heat it up and it will melt. As I heat it up, what's happening is the kinetic energy of the particles speeds up to the point where the arrangement changes. Okay, so the hotter something is, the faster the particles are moving. And eventually they're going to be able to overcome the attraction that they have for each other, because it's almost like a magnet, they stick to each other. They're able to move fast enough that they can kind of escape a little bit, and their arrangement will change. Now, you guys have a little bit of a blank space underneath that in your notes, as well as at the top of the next page. We have a couple of diagrams I want you to draw, and you can draw this first one here at the bottom of page 8. If we take a look at phase changes, okay, we've got our three states. You've got the gas, you've got liquids, and you've got solids. And we can go between these states. I can change from a solid to a liquid, and that of course is called melting. I can change from a liquid to a gas, and when I do that, that's called evaporation. That is not called boiling. That is different. Okay? Boiling is actually a point, whereas evaporation is the process. Now, I can also reverse these. I can take a gas and turn it into a liquid, which is condensation. Great example of that happens with your showers. You know, you've got a nice hot shower going in the bathroom in the morning, and you step out of the shower and the mirror is covered with water vapor. Okay, it's actually liquid water. What happens is the steam from the shower goes and hits the cool surface of the mirror, and those water vapor particles cool down, they slow down, and they actually condense on the mirror surface itself as a liquid. And then I can also turn a liquid into a solid, and that process is of course called freezing. Now there's a couple of special phase changes, and this involves gases and solids. I can actually change directly from a solid to a gas, and that process is called sublimation. Now sublimation is probably best demonstrated by solid carbon dioxide, which you guys know as dry ice. When I take solid carbon dioxide, the dry ice, and I bring it out, instead of turning into a liquid, it basically just gives off this fog-like vapor. So it is going directly from a solid to a gas. You can also sometimes see this in the springtime if we get some intense, you know, in nice sunny days, and it's shining like directly on a snowbank. I know I've seen that before, where you kind of get this fog rolling over the snow. You've got the same thing happening. The ice crystals of the snow are actually sublimating straight into water vapor. And because that water vapor is kind of cool and kind of close to the ground, it turns into almost like a fog. Now I can also take a gas and turn it directly into a solid, and that process is called deposition. And we actually can see this with an element called iodine, which I know you guys have heard of. Iodine is actually a really pretty purple vapor a lot of times, but if you cool down a container of that vapor, you'll actually get crystals directly forming on the sides of the container. So iodine will go directly from the gas state into the solid state. Now if you take a look at these phase changes on a graph, they look kind of like this. And what you notice here is we've got this blue area here, which is where the solid is warming. So let's say I have a piece of ice. Let's just use that because water is something you guys are familiar with. We bring it out of the freezer. Let's say I've got a deep freezer, and it's well below 0 degrees Celsius, which remember is the melting point. So I can start actually warming up that ice. Now it will stay a solid until we reach this point. And hopefully you guys remember that is 0 degrees Celsius, at which point the ice will start to melt. And it will start to melt on this side, and as we go through time, all of it will melt. Notice the temperature does not change. We'll talk about that here in a second. Once it's all turned into liquid, if I keep warming it up, the liquid temperature will then rise. And I can take it up here to this next little plateau, this next little flat space, which is where the liquid is vaporizing, evaporating. And that is its boiling point, which in water's case is 100 degrees Celsius. Then I can, once everything has turned into a gas, then I can take that water vapor and heat it up. Now if I had the ability to, I could heat it up and it would be way off the graph, but I could eventually turn that into plasma. But remember, we can't really create those conditions very easily here on Earth. So why the flat lines on our graph? Why do we have those plateaus? Well, if you notice, the flat spots happen at both the melting point and the boiling point when we're warming it. Now, if I were taking water vapor and cooling it down, we would see the exact same sort of graph, just kind of backwards. We'd start up in the higher temperature range and go down towards the lower temperature range, but we would still see those same flat spots. And they happen in the same points. We just call them different things, like the condensation point or the freezing point. So the melting point and freezing point of a substance is the same temperature, and the boiling point and condensation point of a substance is also the same temperature. Okay? What's happening here is the kinetic energy of the particles doesn't change, and so that's why the temperature doesn't change. What's happening is that the particle arrangement within the matter is changing. So until all the particles have rearranged, the temperature actually won't go up.